As society develops and technology advances, the use of electricity grows more common and its applications progress rapidly. Since we rely on electricity so heavily and it's just getting more prominent, it is very crucial to be educated on the matter. Electricity can do some pretty cool stuff. It can project an image on a TV. It allows you to talk to your friends all the way across the country. But if you really need to get heavy work done, you're going to need something called electromagnetic induction. This little concept was formulated by Michael Faraday and paved the way for converting electrical energy to mechanical rotation. Prior to chapter 16, I knew the fundamentals concerning the inner workings of the electrical motors. With my knowledge in RC cars, I could tell the difference between DC brushed motors and AC brushless motors, and I understood how different winding and wire types affect performance. But I had never even thought about building my own motor from scratch. For my design, I regarded the three-phase Outrunner brushless motor to be the best option that would be most easily manufacturable. This design consists of the coils at the center, while the motor case, the rotor, holds the magnets and rotates around the induction coils. Due to the significantly larger rotor, the motor has more leverage and thus much higher torque, which is very desirable when doing heavy work. Now, as you may know, in the inner workings of a brushed motor, the energy goes through the brushes into the commutator, energizing the coil windings. This creates a magnetic field that interacts with the permanent magnets of the rotor. This generates a rotational force. And now, as the motor spins, the commutator switches polarity, keeping the rotation continuous. Now, a brushless motor uses the same idea. Power is applied to the coil, it generates magnetic field, which grabs the magnets on the rotor, rotates them. But now with a brushless motor, the timing and the switching of the polarity is determined not physically, but by an ESC. And the ESC is typically a little electronic box that plugs right into your battery. Now, since I already had a ESC, which is the brains of a brushless motor, I naturally went for the simpler design of the Outrunner brushless motor. Here's some pretty cool diagrams showing the current and the magnetic induction forces of a brushless motor. Now, I was probably supposed to handwrite these, but these are kind of complicated compared to its brushed motor counterpart, so I hope these two will suffice. I already knew the motor had to be centered around torque so it could move a lot of weight. It had to be large enough so I could build it pretty easily, and it needed to be used with an ESC and battery I already had. With these criteria in mind, I found these designs floating around, which are based on a much larger commercial grade fan or something. I changed a few details so I could press fit a bearing, install the magnets more reliably, and designed a special hub pedestal that I could firmly mount the motor. After all the pieces were done 3D printing, I began winding the coils. Now, I originally used 28 gauge wire that I litzed 50 strands thick so it could competently handle an enormous amount of power. I built the motor and I was super anxious to test it out, but it didn't really do anything. So I went back to the drawing board, double checked everything, and I thought to myself, it's gotta be the wiring. So I built another coil. This time it had more windings per coil, better quality coils, and thinner Litz wire to increase the wire capacity. This one looked by far the coolest, but it didn't fare any differently from the first test. Now, I was super bummed at this point, but I was in a huge rush. It was the day before the final project was due, and I had to get something to work. I remember that the more windings your coil has, the more magnetic induction it creates. So I bought yet another spool of wire, this time 18 gauge, and wound it single layered to achieve a maximum number of layers and wound it tightly around the posts of the stator. And just like the first two tests, it didn't really go so well. It didn't really make a difference, unfortunately. Now, I had really high hopes for this motor. It would be really cool if it panned out, but unfortunately, that wasn't the case. Now, if it did, it would probably produce somewhere around 3.4 horsepower and 10.8 newton meters of torque. That's around 8 foot-pounds. Now, that is over 20 times the power of your little sister's Power Wheels Barbie car. For this little motor, that's not bad. I learned that even though I thought I knew what I was doing, I really don't. Even though the physical design of a brushless motor is pretty simple, there are lots of variables, and even the smallest miscalculation can compromise the entire motor. Despite my failure, I learned how to calculate the resistance and tolerance of wire, how to litz wire to various thicknesses, and how to wind an electric motor. If I tried this experiment again, I would probably use a different ESC. Something was going on there. I don't know if that was my main failure point or if there was something else I was overlooking, but there definitely seemed like there was something off there. Now, I would also probably use a conductive material for the stator and use even more windings on the coils, both to magnify the magnetic force. For those curious, this is the amount of wire I used up, and it still didn't work. Please give me a good grade, Mr. Kwong, and to my fellow classmates, if you'll want to see some ridiculous content, please check out my YouTube channel.